Yes. And then, okay, so we started and yes. So the aim of the lecture for today are that we would like, or we would try to know different types of robotic tools that are attached to a robot flange to perform certain type of tasks or action. I hope you know now what is robot flange. So today I have kept a robot model. So this end of the robot, this is called robot flange, this thing where we mount a tool. So a robot flange and different types of tools that are mounted to the robot flange. Get familiar with robotic tooling systems such as different types of grippers, hands, suction cups, welding tools, painting guns, etc. Introduce tool changing systems that allow to flexibly use different types of tools. Plus, we will also go through feeding systems, and feeding systems are that somehow, I mean, if you have put a gripper at the flange of the robot, but somehow robot need to know where each component is placed or where the component is placed that needs to be poked, that needs to be picked, sorry. And this presenting the components or parts to the robot, or this is called feeding in a robotic language. So we will also see that how different types of feeding system are there, and how flexible feeding can be done. By flexible feeding, I mean that these feeding systems are often rigid. They are designed for only one design of component. And if you want to have different types of components, then there are some approaches to do flexible feeding. So we will also have a look on them. Contents, as I said, that robot grippers and effectors, types of grippers, gripper changing systems, how additive manufacturing or 3D printing is used in robot gripping, and then flexible feeding of parts in robot applications. So to start with, we can classify robot manipulators in 4 different categories. There are some grippers that are used for manipulation. By manipulation, I mean these are the grippers or the tools that we mount at the end of the robot to arm, and they can be used to manipulate some component. By manipulate, I mean they pick the component from one location and place it to another location. So all this pick and place thing, which is the most common application of robots in manufacturing. So all this robot manipulation is done through these different types of grippers. So we can make one class of these manipulation related grippers. Then there are tools that are used for material extraction or some type of machining process, for example, drilling, cutting, milling. These are different types of end effectors or tools that are used with robot for these different machining purposes. A lot of application, particularly in automotive, is joining with robots. So robots do a lot of joining activities, and these are like arc welding, spot welding, gluing. And then there are a few other applications such as painting. Painting is now also done through robots, polishing and sanding. By sanding, I mean if you have casted a component, then there is some excess material on the component after this casting process. And to do this sanding, um, many times robots are used, and that process is called sanding process. So having this classification, we will look into these different types of grippers. And yes, so if we talk about manipulation related grippers, the most common type is which is called two pincher gripper. So Uh, the- when we will do these lectures, there would be a few things that are very old school things, but still we will go through them because yeah, some grippers maybe there are that still do or use these principles, but basically I would say these are old school things, and you would hardly find any gripper in industry that is in the present days is using these type of principles. But yeah, the principle is still there. In the past, companies have been using them. So one example is this two pincher gripper. And this is a very simple type of gripper where you can see that there are two fingers. Here there are claws or jaws that can pick the component. And then there is a cord or wire. And if you push the wire or pull the wire, then due to these springs, they grip the component or release the component. And this pushing or pulling of the wire, this can be done through a motor or any mechanism or maybe some hydraulic method. And this is a very simple type of gripper. Um, and yeah, they can be used. If they are used in present times, then they can be used to pick up small or light objects. So this can be a very simple type of a robot gripper. And similar to the previous one, this is a rack and pinion type gripper. Most of school related projects or educational projects, they use these type of grippers because they are very easy to build. Students can build these type of grippers with additive manufacturing, 3D printing. And it is also with this rack and pinion mechanism. If you push or pull this actuator, so the gripper can be opened or closed, but they are not kind of industrial grade tools. They are more um, hobby related or education or lab work related grippers. Yeah, and then there is this type, which is manipulation tool with vacuum gripping. And these are kind of, they are also manipulating tools, and they are very flexible. By flexible, I mean that because they have some suction cups, and if you can see these previous types of grippers, they can only pick a certain type of component or component with a certain shape, maybe a screw or maybe a pen. But if I want to pick, for example, this smartphone, maybe this gripper cannot pick it. Maybe it will slip even if this gripper picks it. However, these vacuum grippers, they, as you can see their shape, they are very flexible. So this vacuum gripper only needs to get attached to the smartphone and then suck it up, and it can hold it. So these are more flexible. Conventionally, how they are used, that at the end of the robot arm, you have this kind of tool, and at the other end, you have a pump, and that pump creates this vacuum. And as long as you have a vacuum in your tool, the robot can pick up the component. However, there are these new tools. For example, this tool doesn't need a pump at its end, so it has the whole mechanism in, in itself, the gripper. However, for example, on the right side, this tool requires a pump on the other hand, and that pump will enable or will provide the gripping force. So there are new developments as well in these gripping or vacuum grippers. There are some challenges with these grippers as well. For example, they can create or they can put some gripping marks on the component if it is some sensitive component. So you have to take care for what type of components you are using them. There can also be, for example, some because there is a pump on the other end, so it is not that you are getting a constant force all the time. there can be some variability. And if there is a problem and the robot is carrying maybe a very heavy component, and there is some problem with the pump, it can drop the components. So in case of an accident, you can have a big accident. So these kind of challenges are associated with these vacuum grippers. However, due to their flexibility and ease of building these grippers, they are used a lot in manufacturing applications. And then there are more these kind of grippers, which are also vacuum grippers, but they are more flexible. As you can see that they don't have any a permanent shape. Rather, they just fit into the component that they need to pick, and then they create this grip vacuum and then pick the component. And they are called more flexible or for uneven shaped parts. Um, as I said, that they also have issues with surface types, can leave marks on some surfaces. Decreased reliability, as I said, that there is another component which is a pump connected with them. And if there is a problem with the force that it is providing, the gripping can release the component. And if it is a very heavy component, then you can damage the component, or there can be an accident for the worker or the operator. So these kind of challenges are there. Problems with compressed air. If you are using compressed air, so you have to use some safety standards, because compressed air can be dangerous. So you have to comply with many safety related things if you're using compressed air near to humans at a production floor. But this is one type of grippers that are being used in manufacturing applications. And then there are these pneumatic grippers. So I'm going through some most common types of grippers, and then we will also see some classification of them. Most popular type, due to its compact size, lightweight, and force, they can easily be integrated into light work cells, which can be handy in manufacturing. You will find most of the grippers that are used in manufacturing applications to pick small components with 2 fingers. They are mostly pneumatic grippers. And then there are these hydraulic grippers. They provide the most strength or most gripping force to pick heavy components. They are mostly used for these large robots and not really suitable for small robots. And to pick large components, heavy components, these hydraulic grippers are used. So in terms of hydraulics, there is some oil that is from pump. They create the pressure by which a hydraulic or a picking force is generated. But because there is oil used in these pumps, and they may damage the end effector with high force. And I would say that this is also something that you would really rarely see in manufacturing application, because it is something that is used for only for very large robots, and also where the damage to the surface of the component doesn't really matter, because you can't really control how much force it will apply on the component. It can vary during applications, and due to that, it is not suitable for any component that has some fine finish and that can get damaged due to the gripping. However, this is another type of grippers that are used in manufacturing. And then there is this type of servo-electric grippers. They are different from those pneumatic grippers or the grippers that we have seen before. The difference is that those grippers are more binary kind of grippers. So there is 0 or 1, open and close. When you will integrate those grippers with robots, you will see that you define either the gripper is closed or either it is open. So 0, 1. However, in these grippers, there is a motor, and then there are wires that are connected to these fingers. And when the motor turns in one direction or other direction, and it pulls or pushes the wires, and due to that mechanism, the fingers get open or fingers get closed. Due to this mechanism, they are not suitable for heavy components, but they are rather more suitable for light components that can be, when I say light, of course, it is not an exact value that for how much weight we can say light, but roughly I would say that maybe if it is up to 2 kilograms, then it is suitable. But it really depends still on the shape of the component or on many other parameters, and also the size of the robot arm, etc. Okay, we have gone through these basic types of grippers, and we have seen how these different types of gripper work, what are different mechanisms that are employed in these different types of grippers. And if we talk about these manipulating grippers and different grippers with different number of fingers, we can see that they can be further classified into 2 fingers gripper, 3 fingers gripper, 4 finger gripper, or a robotic hand, which is very similar to a human hand. The thing is that if you have, the more fingers you have, the more flexibility you will have. When as a human we are going to or we want to grasp some component, we humans have a very high degree of dexterity in our hands. Our hands are very flexible, and we can shape them or in depending on the component that we want to pick. If I want to pick a pen, my brain tells to my hand to how to pick this component. I will not pick this component like this, but rather I will pick it like this, or any shape that is suitable to pick this component. If you need to pick a paper, your brain will immediately tell to your fingers to pick it with 2 fingers or 3 fingers. If you want to pick a heavy component, you will pick it with 2 hands. So all this program is already programmed in our minds, and we know how to do it. However, robots don't know this, and they need to be programmed according to the shape of the component that they need to handle, that how they should handle it. And you have to decide that which gripper should you use. Should you use 2 finger gripper, 3 finger gripper, 4 finger gripper, or you need more flexibility and you should use a robotic hand. The more fingers you have, the more flexibility you will have. By flexibility, I mean, if you are using 2 finger gripper, there will be only very few shapes that you can pick. For example, if you have this component, maybe this 2 finger gripper will not be able to pick this component. It will be very difficult. If it is placed like this, then maybe it can pick it from here. But if it is placed like this, then it cannot pick it. Maybe then 3 finger gripper can pick it from a different orientation. A 4 finger gripper will provide more flexibility similarly. So why not we always use a robotic hand, which is more flexible, or always use a 4 finger gripper because it is offering more flexibility to handle more types of components. Can anyone make a comment that why don't we go always for a more flexible gripper and not to go for a 2 finger gripper? However, in industry, mostly 2 finger grippers are used.
Expense.
Exactly. So the most important thing that will come into play here is the cost. The more flexible gripper you have, the higher cost it will incur to integrate it. So 2-finger grippers are least expensive, then 3-finger grippers, and then 5-finger grippers are very expensive. And when you will be required to select a gripper, the cost will be a very important factor that you will have to consider. Yeah, here I had tried to put different types of or different parameters or properties of these grippers. I will show you a tool that is used to select gripper based on your application or based on the properties of the component that you want to manipulate. And yeah, I will discuss that tool later today. Yeah, and yes, then as I said that we humans know how to pick the components, and at the same time we also have an ability that when we are picking some component or we are performing some task, we adjust our hands or adjust our fingers to or apply right forces to perform that task. For example, if you are placing a key in a keyhole, you we exactly move our fingers to fix the key in the keyhole and it gets fixed. But robots don't have these properties. However, modern robots are getting sophisticated, and there are these torque measuring tools available in those robots. But still, you need to do programming in a very precise way to make them unable to do these tasks. Also, there are some new AI-based algorithms that are being developed to make robots get learned or self-learned so that after performing hundreds of the same task hundreds of times, they get to know to where to exactly place the component that it will exactly fit in where we want to place it. But since robots don't have these, in principle, they don't have these abilities available, and we want to use different types of grippers or different types of tools with the same robot to perform different types of tasks. One thing is this. The other thing is the robots are quite expensive. They are not a cheap tool. Even if you want to buy a very small robot, you should be considering like 100,000 or 200,000, only the robot arm. Then the other setup, the grippers, the maybe safety related tools, that is all uh, uh, they also have other costs. So you can't do this that if you want to perform 3 or 4 different tasks, you buy 3 or 4 different robots. Rather, you will go for some tool changing methods. But again, it depends on the application that you are using for the robot for, that if you can use the same robot for 3 or 4 different tasks. But can you change the robot tool every time? I mean, for 10 minutes, you use a robot for one task, then for the next 10 minutes, you have to use robot for another task. But can you do it manually? Of course not. It will take quite some time to remove one tool, put another tool, then remove that tool, put the next tool. There will be some screws that need to be opened that get fixed. So to automate these activities, many companies are now offering these tool changing systems. So what these tool changing systems are, that they are often consisting of 2 parts. One part is attached to the robot, the other part is attached to the tool or the gripper. and they have some kind of mechanism of joining, maybe a hydraulic or um, some snap fit, or some mechanism that they both components can get joined. And due to these features, they can be uh, easily attached or detached, and hence they provide you a flexibility to to use different types of tools or different types of grippers with the same robot. Yes. For example, here you can see that this robot, there is one component that is attached at the end of this robot, and then the other component is attached to the gripper. So now this robot is using this pick and place two finger gripper, then it detached this gripper, attached to another gripper, and now it is a vacuum gripper. This is advertisement. Okay, and this is this component. Um, so they can be, this is one component that is attached to the tool, and then there needs to be another component that is attached to the robot, and this provides this attaching and detaching of components and make it the tool changing more easy. And the same thing is with these for large industrial robots. For example, this Fanuc robot, this is more an more industrial robots. This is also industrial robot, but depending on their classification. So this Schonk is a German company that that is well known for robot grippers. They manufacture robot grippers, a whole range of robot grippers. If you are familiar with lean methods of production or lean techniques that are used in manufacturing. So in lean techniques, there is one concept that is called SMED, which refers to single minute exchange of die. And what the concept is that when you are changing the tool of any machine, it should be done at the minimum time possible. And the concept is coming from Toyota production system, where they implemented some technique that and they reduced the tool changing time considerably as compared to other companies. And from there, the concept is coming. So in terms of robotics, we can say that this tool changing method or these tool changing devices, they are aligned with this SMAT concept because they are enabling us to change the tools without having any effort to have a screw driving tool to open the screws, close the screws, change, get aligned with the new tool. So this all tool changing thing can be done more automatically with these tool changing devices. And this is aligned with this lean concept of SMED as well. Okay, aligned with these lean techniques of manufacturing, there is another Japanese concept, which is about low cost automation, that when you are doing automation, you should try that the automation is not expensive. Rather, it is cost effective or cheaper, we can say. And the Japanese word for that is karakuri. And this refers to low cost automation. How we are implementing, or the new approaches of implementing this in robotic automation, is that when you buy a robot um, gripper, often if it is, for example, a two-finger gripper, there will be some two small fingers at the end of the gripper. Of course, it will not get fit with all the components that you want to manipulate with the gripper. So what the approach is that people manufacture, or the companies manufacture end effectors or fingers. We call them end effector or finger, and these fingers are many times machined. uh, they are manufactured with milling or any appropriate manufacturing process. But if they are machined, it takes a lot of time and they are more expensive. So the new approach is to, what if we use 3D printing to develop these kind of tools? And at least at the development phase, they provide a good solution to quickly develop these tools that are developed or manufactured with 3D printing or additive manufacturing, and they can be either used with 3D with a robot gripper. For example, here it is attached with a gripper, or then these tools are also developed with 3D printing, and the robot can pick these with its fingers. In case of this robot, the robot needed to pick or hold some lasers. So this whole component is developed with 3D printing. If we had tried to develop this with machining out of aluminum, maybe it could have become um, more expensive and would take much more time. So, this is one technique that is being used quite a lot in manufacturing applications to make these fingers or end effectors out of additive manufacturing. And the purpose is to reduce the development time as well as the cost. Of course, the life of these tools is less if you, as compared to aluminum or machined components. But as I said, that at least in the development phase, they provide a good solution. Once you have finalized the design, everything is decided, then you can go for more uh, expensive tools. But at least for many applications, they are a good option to replace machined components or machined end effectors. So until here that we have discussed these different grippers. Okay, one thing that I would like to show. Yes, I would encourage you. I don't want to make an assignment out of it. Um, Actually, I would like you that you develop this kind of tool for yourself. Maybe I can share this with you as well. The thing is that if you are working with a company, or if you are assigned a task to implement a robot, um, there is one big task when implementing robot to decide the right gripper. That how would you decide that which gripper is used? Of course, there are people or consultants who have a lot of experience, and they can tell you which gripper should be used by just with their experience, because they have all this information in their head. But particularly for a new company that is into automation, or for a person who is a little bit new to automation, it is a great idea to have this kind of tool where you can, depending on the component that you want to manipulate, or the task that you want to perform. Here in this case, we have assigned scores that based on these measures. For example, if we take example of this component, then uh, pick contact area. If it is a large area, small area, or if it is just a point contact. So how much space do you have in the component to pick it? And based on that, you can assign a score. For example, here I say that it is a small area. For small area here, we have assigned a score 3. Of course, these numbers are relative and they can be different for different people can assign different numbers. But in this case, a lot of people or experts or technicians, engineers, they gave their input, and having input from all those people, we assigned these scores. And then pick flexibility. How flexible is the component? Pick weight. If it is less than zero point 0.1 kilogram, zero point 0.1 to up to 0.5 kilogram. For example, here I have 3 score. Pick speed, holding stability. So if you assign scores to all these things, then we can see, depending on off-the-shelf grippers, if you are not going to manufacture your own gripper, if you find off-the-shelf gripper, then we can see a score that it has assigned to different grippers, and you can decide that which gripper should you use for your particular application. And here I can see that, for example, the numbers that I have assigned, it is showing me highest score for this 366 for that I should go for this gripper. And I think it makes a lot of sense. If I am going to implement a robot that should handle, for example, this component, I would also go for a suction cup, because it can pick it most easily as compared to any fingers-based gripper. You can also develop this kind of tool for yourself, and I am sure if you are going to work in the field of automation, or if you are going to do some automation project, this kind of sheet or this kind of tool will really help you. Okay, the things that we have discussed so far, do you have any question, or do you want to discuss something with regards to them? Okay, so the next thing that we would like to to explore is the feeding of components when implementing robots. So as I said, that somehow the robot needs to know where the component is placed that needs to be picked and where it should be placed. Um, for small components, this is a conventional approach, a very old approach of aligning the components or presenting the components to the robot. These are called bowl feeders. And with these bowl feeders, here I am only showing the performance of these bowl feeders, but at the end, a robot is placed and the robot pick each component one by one that is coming out of these bowl feeders. And these are vibratory bowl feeders. So they vibrate and they make the components in in the same shape. Here you can see they are coming in the same orientation. And then the robot from each point, it picks the component and places it where it needs to be placed. But these bowl feeders come with many challenges. The biggest challenge with them is the cost, because it takes quite some cost to manufacture them. Then it is only for one shape of component, only for this shape that it is handling. If you have a change in the design or a different shape, then you need another bowl feeder. And for example, if you have 15 components in your product, maybe it is a small product, then you need 15 bowl feeders. And it is not really a great idea. But yeah, until now, or until recent past, this was the most reliable way of presenting the parts to industrial robots for with these small components. And yeah, they are still being used a lot. There are some new approaches also into them, that some people have started to 3D print this top component. So if you have a change in the design, so the remaining component remains the same, but the top component is, if it is 3D printed, so they replace it with another 3D printed component, which is of course cheaper than these metallic components. One other big challenge is that they require large space. So if you have 3 or 4 components, you need 4 bowl feeders, and they will take a lot of space in your work cell or robot cell. So companies always try to discourage the use of them or try to avoid them. But if no other solution is available for that particular component, then they have to go for it. In this example of robot application, we avoided to use any bowl feeder. Instead, we placed many fixtures. So for each component, there is a dedicated fixture, and the robot. So now we started the robot. And from each fixture, one fixture, second, third, fourth, fifth, it will pick components. But again, the problem will remain the same, that each fixture is for one particular shape of component. And if there is a change in the design, you need another fixture to be manufactured. So these are some of the challenges that are there with the robotic automation from last 20, 30 years, and they have they still are unsolved problems, I would say. There are approaches to solve them, but there are not really great approaches to solve them. There are some solutions that can reduce the effect of these problems, but cannot really solve them. Yes. And at the end, you can see that these are robot fingers. So basic gripper is something only this, but that you buy from a company that manufacture grippers. And then these fingers you manufacture by themselves or from some other company. And they are just screwed to the gripper. And now you can see that to perform this task from the robot, you need all this setup. And if there is a small change in the position of any of this fixture, if I move it 1 centimeter away, then the robot will not be able to pick that component. So it always should remain at the same location. And hence we say that there is no flexibility. These are kind of rigid automations. So what are the new approaches or more innovative approaches to create a degree of flexibility in them? Yeah, so flexible feeding is to integrate some type of cameras or vision systems that can detect the parts, know its orientation, know its position, and then communicate that information to the robot. And the robot adopts its fingers or gripper fingers according to the location and orientation of components. It is all about location, locate and pick parts, locate and move relative to parts for assembly. Yeah, and if you can have some vision systems or some cameras that can detect the location and orientation of components, then they are relatively cost effective as compared to those mechanical fixtures or mechanical bowl feeders. They are easier to implement and they are adaptable to many different parts. But um, there are, okay, I will discuss it later. So there are some benefits of using these vision-based feeding techniques. And they are all this feeding discussion, this is very much closely connected with the grippers discussion, because gripper is something, or gripping is something to pick the component, while feeding is something to present the component to the robot to pick it with a gripper. So this feeding is all very much connected with the gripping discussion. Okay, I skipped this. And here you can see that now the robot is, for example, if actually all are playing at once, but just look at, for example, this first one on the left side. And here you can see that if we place different components in front of the robot will know. So now the operator has randomly placed them, and the robot will know where. It knows that first it need to pick that component, that wheel, and it got the information because there is this camera on top of it, and the camera communicated the information that where this component is placed, and then the robot picked that component. In this example here, you can see that there is this plane which drops these components on the plane. They vibrate it, and by vibration on top of it, there is a camera. And then the camera communicates the information to the robot for the location of each component. And now can see that in this case, you don't need any fixture. You don't need any bowl feeder. Rather, there is some camera mounted on top of the robot, and that camera is communicating the location of the components. And then there are, of course, the cameras are also based on different principles: 2D cameras, 3D cameras, then 3D plus CAD cameras. I will not go much into this detail, but just a very high level introduction. I mean, 2D cameras are only that see the component from top. And if you increase or decrease the distance between the robot and the components, then it will not understand that the distance between the robot and the components. So it only measures the X and Y values. While 3D cameras are 3D cameras, they measure the position and orientation of components in 3 dimensions. And when we say CAD enabled, they employ an additional feature plus 2D camera or a 3D camera. So additional feature is that in the memory of the camera, you have also placed CAD 3D model, CAD, computer aided designed model of the component in the camera memory. And the camera looks at the component plus matches it with the 3D geometry of the component, and hence it more accurately identifies the component. But the more features it will have, more time it will take to to identify the right component. And of course, time is all about money when we talk about industrial applications. So you really need to carefully decide that which application should or which technique should you go for when you are deciding the camera. Uh, the cameras are also quite expensive. Even a 2D camera, this is the cheapest camera, quite good with 2D techniques. But I remember the values in euros, but not in US dollars. So, but roughly it should be around minimum 2000 USD. But 3D cameras are much more expensive. Yeah, there is a project that we did to see that how these different techniques can be compared with one another. So just based on the cost effectiveness, ease of configuration, cycle time, just to have a view that how these different techniques are compared, and we could see that almost these are off-the-shelf solutions for vision cameras for flexible feeding, and we had some results that almost all the cameras were able to pick the components that we have used for testing. Um, this Picket 3D camera was least accurate, but the biggest differentiating factor remains, to my understanding, there are two factors that come into play when deciding. One is cost. As I said, that some of these cameras are very expensive. And the other thing is ease of integration or ease of reprogramming. So that is also a very big challenge. I mean, if you have integrated the camera, you have programmed it for one type of component, but then and it can often happen in companies or in manufacturing that you have a change in the design. You have maybe no, maybe a small change in the design, maybe a large change in the design, or maybe you want to use for another application. And how easy is it to reprogram it? How much effort it will take? And this effort is often measured in terms of time. That do you need a day to reprogram it? If you need a week or a month? So it is always a good idea to go for a solution that is easiest to reprogram it. Or sometimes companies need some other company to reprogram it. And if it is another company to reprogram it, or system integrators, and oftentimes there are system integrators that do it. And then, of course, it will add a lot more cost into the project. So these different factors come into play when you are deciding a gripper or a feeding system for those grippers. So this is a quick discussion on these grippers and feeding systems. Uh, there will be more things that you will go through from the handouts that you will find at Moodle, and you will see that there are some other parameters as well that are important when we are talking about grippers or and effectors or vision or the feeding techniques. So any questions so far? When you are mounting the cameras, there are different techniques again associated with that. I mean, you can mount a stationary camera on top of the components, and there are components on the table for maybe, for example. You can also mount the camera with the robot, and these are different things that you decide based on your application. And here you can see that if it is if the camera is mounted with the robot, then the cycle time is long. Can you guess why the cycle time is long?
I feel like it has to stabilize the camera before moving it again.
Yes, that is also correct. And also because it will find the right component, it will pick it, and then will move um, to some other direction to place it, to assemble it, to mount it somewhere. And during that time, it is not doing any job. The camera is not doing anything. Then it will come back and will look again on the components, and then will uh, uh, communicate the information for the next component. However, the advantage is that the camera can go to many different locations as far the robot arm can go, but it will take more time to find each component. However, if you place a stationary camera, for example, then it is looking only at a limited space, but it can the cycle time is short because the time the robot is performing some other task, in the meantime, camera can find the next component. And as soon the robot comes back to pick the component, it already knows that where the next component is placed. So these are a few other things that you might need to consider when you are implementing grippers or vision systems. So in the next class, we will be doing some robot modeling. And for that, we will use, primarily, we will be using Technomatics software, Technomatics Process Simulate. You can access the software remotely from your homes or from your personal computers. You can also access the software in the computer lab that we have at the 5th floor, the PLM lab. So maybe in the next class, I will not give an assignment related to the software because but in the next week, you will definitely have an assignment based on that software. So you should be able uh, to get access to the software. So you may be a good idea to already try out if you can get access to the software. The name of the software is Technomatics Process Simulate. And yeah, so we will be using that software. In parallel, we may need to get help from some CAD software, for example, SolidWorks or NX, whichever CAD software you have access to, or you are familiar with, Inventor or any software. If it is NX, then it is the best because it is more compatible with Process Simulate. But if you have any other software, that is also fine. From today's class, I will upload a document for you to study. The documents that I have uploaded so far, there have been 2 documents so far that you have been given for study. It is a great idea to go through them because when we have quiz, then there will be some questions from those documents. So I would highly encourage you to go through those documents, and it will really help you to better understand what we have discussed so far. I fully understand that these are very, very practical things, and they will make much more sense when you will practically do them. So theoretically or only listening to these things, it is okay. It is making some sense, but once you will also when you will start modeling them in the simulation, and when you start modeling the robotic processes in the simulation, you will need to know many of these concepts that we have discussed today, the ones that we had discussed in the previous lecture. So many of these concepts will be incorporated into those simulation development. A lot about robots, because when we will develop the robots in the simulation, or we need to define the grippers, we will need to define all these things. like where robot fingers, gripping entities, different shapes of grippers. Sorry. So all these things are very important before you start building the simulation in Process Simulate. So any question from today or anything that you would like to discuss?
Professor, when we get back into, first of all, I love the videos that you provide. They're very helpful in understanding of where everything is moving and make sure that I know like where things are attached to, especially with the camera too. When we get back in person, would you be able to still record these lectures just so I can have them at a later date so I can go through, pause, and take notes properly?
So you mean if we will record them or not?
Yeah, so when we get back in person, usually in a lot of the classes, I don't know if it will be in this classroom, but there will be like a webcam or some sort of like microphone that you could just like put on and then just record the lectures while you're teaching in the actual room.
Okay, so if I have understood your question correctly, so it is about when we will get back to classroom teaching.
Yes.
Okay, that is something that so far we have been told that it is only until end of January. And from
Yes.
first week of February, we will be back to classrooms and also to the labs. So this is the information that we have been communicated so far. And I have this plan that from 1st of February, we will be back to the classrooms.
Perfect. Okay, great. Thank you.
You're welcome. And yeah, and then we have already started to set up the lab. It is already set up, but just to prepare it for the experiments. And also, as I said, that planning to buy a new robot or a couple of new robots, let's say. But yeah, so lab experiments would also be there. And they will be very much connected with the simulation software that you will work on. So I would really like you to maybe during the classes, we will do some practice with the simulation software, but I would really like you to get expertise in the simulation software, because believe me, when you are doing a bachelor or a master, there are some courses that that can give you there are some courses that build a foundation of you, and then there are some courses that you can really make a job out of them, or you can make some money, or you can make a job solely based on that course. So I can tell you that this is one course, the things that you are learning, or you will learn, that you can make a job out of them. So these are the things that companies are struggling with. There are many companies that are trying to do these things. So if you know these things, if you know how to do robotic simulations, if you know how to do some basic programming, if you know how to select a robot or how to select the right gripper given the components, and if you can make a schedule for how to integrate a robot. By schedule, I mean a framework that what activities are involved in implementing a robot. These are the things that a lot of manufacturers are struggling with. So these are really useful things. And as I said, the simulation is really a useful tool that will really help you in your practical work. Okay.
Great. Thank you.
I will upload this Excel sheet as well at Moodle. I will make some changes to it, but I will upload this sheet. But I would highly encourage you that you develop your own tool. Get inspired from it, take some learnings from it, how they have done it, because this is, I guess, 2 years old, and in 2 years, maybe you will find new grippers that you can. I know there are new grippers. These are 2 years old grippers, and now there are some new technologies as well. So you can really make your own tool and then decide that how to select a gripper given the components, and then just play with it. Find different components around you. Just look at your table and find different components, and then decide if you want to pick and place this component with a robot arm, then which type of gripper should you go for? Or if there is any new technology, if there is any new gripper that you should go for. These are some big companies that manufacture grippers. Schonk is one company from Germany that manufacture grippers. Robotic is another company. Then there is On Robot, one company that manufacture grippers. And this Festo is also an automation company. They develop a lot of components, but they have a lot of interest in robotics based on um, uh, bio-inspired robots, bio-inspired tools. So all if you will see their robots, you will see that they are inspired from some animal or some feature of some animal that they have incorporated into their automation tools. So yeah, so the reason for telling these different companies that if you look at their websites, you will find many new tools. They are very innovative companies, and you will find many new gripping tools. Uh, Probably, or I'm sure you will not find any gripper that will look like this. But as I said, that these are some things that come into theory and we just discuss them, but modern approaches are very different from them. Okay, so just to sum up, we studied the grippers today, different methods of gripping. Then we saw tool changing methods. And then finally, we saw how parts are presented to the robots, that is called parts feeding. And then there are new approaches of vision-based feeding that we also call flexible feeding. You will also get a handout for reading in your at Moodle, and you will also have this Excel sheet. But again, try to develop your own Excel sheet or a gripper changing tool for your own use. I don't want to make an assignment out of it. And in the next class, try to look into that. If you have access to Technomatics process simulate software, we will start using some of it from the next class. So this is all from my side for today. If you have any question, feel free to ask. Otherwise, you are free to log off. But thank you. Thanks again for joining this class.
Professor, are some of those videos, I know that some of them are you, like